Welcome to this video series on how to design an impact wrench adapter for use with a cordless drill. In the previous video we modeled the parts in NX and put them together in an assembly. Now that the 3D model is finished, it is time to do a dynamic simulation in Siemens NX to check if the mechanism functions correctly and to predict what the output torque and impact rate will be. To set up the simulation, we must follow the steps listed here. First, we open the assembly and start NX motion. Then we have to define which components from the assembly we want to use as motion bodies in the simulation. The next step is to add the joints to the motion bodies, which enables the components to move relative to each other or in the coordinate system. We also have to manually define a spring connector to simulate the spring force. We must define the 3D contacts that cannot be specified with joints, such as the hammer impact on the anvil and the contacts with the balls. Then the loads have to be specified, which is the motor torque in this instance. The last step is to set the solution attributes to run the simulation. Now we can play the motion simulation and view the results. In the assembly, we go to Application and click on Motion. On the next screen we click on New Simulation. Give the simulation file the desired name and folder and click OK. Now we must specify the environment. Select component-based simulation if you want to use the geometry and mass properties of the parts in the assembly. Joint Wizard can be used to automatically detect motion joints from an assembly, which can be useful. We want the kinematics to be converted from the assembly constraints. In the Joint Wizard we can select the joints that we don't want and disable them. We will disable most of them, since we are only including relevant components in the simulation and exclude the housing, bearings, and spring. These are the motion bodies and joints that are imported from the Joint Wizard. Let's first make most of the parts that are not needed for the simulation invisible. Next, we need to define the motion bodies that were not imported from the Joint Wizard. This can be done by clicking on Motion Body and selecting the part. The mass properties are set to automatic, so the properties are derived from the CAT model. Click on Update Display Values to ensure the values are correct. If you have not assigned a material in the CAT model, then the mass properties for steel are automatically applied. It is also possible to fix the motion body without joint in these settings, which is what we want for the anvil. You can change the name of the motion body, so it is easy to identify later. We repeat this for every motion body that is not yet defined. In the next step we must define the joints between the motion bodies that have not been imported from the Joint Wizard. The cylindrical joint is already applied by the Joint Wizard to the flywheel and driveshaft. This allows both rotation and sliding. To the driveshaft we need to manually add an revolute joint to only allow rotation around its centerline as it's supported by a bearing and the square tool drive. In the simulation we do this by clicking on Joint. Now we need to select the type of joint we want. The action body is the driveshaft, and we also need to specify the origin in the center of the shaft and the revolute axis along the center line. As base body, the anvil is selected, since this motion body is fixed in the global coordinate system. To the spring holder, we also manually need to add a fixed joint with the drive shaft as base body. This means that the spring holder will rotate with the drive shaft. To simulate the spring, we must add a spring as a connector. The attachment is to a motion body, with the action motion body being the flywheel and the base motion body being the spring holder. The spring parameters that we have chosen in the second video are used for the input values, which is a spring stiffness of 21.16 Newton per millimeter and a preload of 210 Newton. Since the spring is a compression spring, we set the application direction to compression only and click OK. To be able to simulate the impact and ball connections, we also have to define 3D contacts. For the contact between the flywheel hammer and the anvil, a cat contact type is used. The action body is the motion body, which is the flywheel, and the base body is the anvil, which has no degrees of freedom. We also have to fill in some parameters that are dependent on the materials and application. These values are normally obtained from empirical data. Since we don't have this data, we can click on this question mark and use sample values that are provided in guidelines for contact materials from the Siemens NX documentation. The hammer and anvil are both made from steel, and we will also be adding grease, so we use the values listed in the second or third row as starting point. In this case, the correct values are already filled in. The balls come into contact with the drive shaft and flywheel. For this, we use a sphere to cat contact type. The sphere is of course the ball, and the body is the drive shaft. The radius of the ball is 2.5 millimeters. For the parameters, we use the same values as for the contact between the hammer and anvil. We must specify this contact twice for each ball, with the drive shaft and with the flywheel. To simulate motion, there must be something that drives at least one motion body. The easiest way is to define a driver, but this is limited to only displacement, velocity, and acceleration. What we want is to imitate the speed-dependent motor torque to check if our mechanism functions correctly and to calculate the impact velocity. We can do this by defining a scalar torque load. The scalar torque is to be applied on a motion body, so we select the drive shaft. The torque is to be applied around the z-axis, and the application type is action only, so we don't have to define a base body. For the magnitude, we choose function as type. Now we go into the function manager and click on New to define our equation for torque. In the second video, we derived an equation for the speed-dependent motor torque, which we will be using here. We will also be using an if statement here, because we don't want a torque higher than the stall torque if the drive shaft turns the opposite direction and the angular velocity becomes negative. For this statement, we also need the actual rotational speed of the drive shaft, so into the formula we insert a derived variable. We select velocity as observable, and under component we choose RZ, which is the angular velocity around the z-axis. To insert the variable in the equation, we can double-click on the revolute joint of the driveshaft in the list. In the formula we fill in that if the angular velocity of the driveshaft is more than 0, then the torque equation applies, which is 12.5 Newton meters minus 12.5 Newton meters divided by 157.08 radians per second times the actual speed. For the actual speed we again use the angular velocity of the driveshaft. If the angular velocity is not more than 0, then the torque is equal to the stall torque, which is 12.5 Newton meter. Always check if there should be a plus or minus sign. This depends on the orientation of the coordinate system of the derived variable and the global coordinate system. Don't forget to change the units to Newton meter. Now if we click OK, we get an error that tells us that we must use the same dimensions in the formula. To work around this error, go to File, Preferences, Motion, and all the way at the bottom select Ignore Units. Now go back to the function editor and save. The last step is to define the solution attributes to run the simulation. In this screen you can choose options and input parameters for the solver. In principle, you don't want to change the standard settings if you don't know exactly what you're doing. Also, only change one parameter at the time, because if you get an error message or the simulation won't run well. I am also no expert, but I iteratively found that the following settings work best for this simulation. Under Analysis Options, we set the solution end time to 0.2 seconds, because this should be sufficient to simulate several impacts and it reduces the calculation time. We won't include static analysis, since we are only interested in the dynamics. We also select No Gravity, since this has negligible effect on the dynamics of this mechanism, and in reality the mechanism will also be randomly orientated. Under Dynamic Options, we select that we want the reaction forces at each step to evaluate the impact torque. We change the print method to actual, so the reported force is at the actual time step. Now we click OK and click on Solve to start the calculation of the simulation. When the calculation is finished, you can click on Results and play the motion simulation. Depending on the simulation step size, it might be better to increase the animation sampling rate to speed up the animation. This animation looks promising as the mechanism seems to work correctly and as expected. Now we can also evaluate the more scientific data, such as the flywheel speed at impact, the torque provided by the motor according to the equation, and of course the output torque on the anvil. If we want to see the angular velocity of the flywheel in a graph, we can click on the flywheel motion body and extend the XY Result View tab. We click on plus of velocity and double-click on RZ, which is the angular velocity around the z-axis. If we click on this icon, it opens the time graph. The units are in radians per second, So if we double-click on this axis and change it to revolutions per minute, we can see that the angular velocity before impact actually increases to almost 2000 rpm instead of the maximum motor rpm. This is because when the spring is released, the potential energy is partially converted into rotational energy by the slope of the V-grooves. If we select the torque load and again go to the XY result view, we can click on forces and double-click on TZ, which is the torque around the Z-axis. As you can see, the maximum motor torque is 12.5 Nm at the start and doesn't reach above 10.5 Nm during continuous usage. Theoretically, it even decreases to -1 Nm when the spring energy is released and the balls impact the bottom of the V-groove, shortly increasing the speed beyond the maximum motor RPM. We are most interested in the output torque. We can view this by selecting the anvil motion body and, similar to the motor torque, go to XY result view, click on forces and double-click on TZ. The units in the graph are in Newton millimeters, so we should change this to Newton meter. Having done this, we can see that the peak torque at impact is almost 4,900 Newton meter. Intuitively, this seems a bit much, and from the animation it also seems that the hammer doesn't bounce as much from the anvil as I would expect. To correct this, we must go back into the 3D contact settings and lower the material damping by a factor of 10 as recommended in the Siemens NX document center. I did this twice, because lowering it the first time did not change much for the bouncing. Now solve the simulation with the new parameters. After rerunning the simulation and playing the animation, the bouncing after impact seems more realistic. We again open the torque graph of the anvil. We see that the maximum torque is now reduced to a little over 220 Newton meter. This value seems more plausible and the animation also seems more realistic, but validating this result requires actual testing. Loads that are obtained from the dynamical simulation can be used as input for FEA strength analysis. The main concerns to analyze would be the contact stresses in the V-grooves and the surface between the hammer and anvil. This has not been done for this particular project, since we are making a prototype and do not have hardened steel with the desired properties anyway. In case of production for actual use, FEA should be done to evaluate wear and lifespan. In the next video, the parts will be manufactured and assembled. The adapter will then be tested to see how the mechanism performs for practical use.